Hi, this is Brandon Baines in the math department at Lipscomb University, here to talk with you today about linear programming. In this presentation, you'll learn how to find optimized values of a given quantity using linear programming. Linear programming is a method for solving optimization problems. These are problems in which we're looking for the highest or lowest values of a variable, in which this variable is constrained by other factors. So in some everyday scenarios, we may be interested in things like profit. And in that case, we're interested in finding the highest profit. However, if we were in manufacturing and we were keeping track of the number of defectives that we were producing, then we would hope to minimize the number of defectives. And so each of those things may be constrained by several other factors. And so this is what forms our constraints, and our objectives are the things that we're wanting to either maximize or minimize. So again, the function that models the variable to be optimized is defined to be the objective function. And all of the constraints form a system of inequalities. And in order to find an optimized value, we're going to have to select from the solution to the system of inequalities. In linear programming, the graphical solution to the system of inequalities is called the feasible region. Here's an example scenario. A certain aircraft can carry no more than 60,000 pounds. The aircraft is used to transport bottled water and medical kits for disaster relief. The bottled water weighs 20 pounds per container, and the medical kits weigh 8 pounds per kit. Each plane can carry no more than 6,000 containers and kits altogether. Each container of water serves 10 people, and each kit serves 6 people. Determine the number of containers of water and the number of medical kits the plane should carry to maximize the number of people helped. The objective function, we'll call it P for the number of people helped, is P equals 10x plus 6y, where x is the number of containers of water and y is the number of medical kits. This is our objective function because the number of people helped is the quantity we're wishing to maximize. And we know that for each container of water, we help 10 people, and for each medical kit, we help 6 people. The constraints in this problem are x is greater than or equal to 0, where x represents the number of containers of water. Y is greater than or equal to 0, where y represents the number of medical kits. So it's simply saying that we are either going to carry 0 containers of water and up, and we're going to carry 0 medical kits and up. Our other constraints are 20x plus 8y is less than or equal to 60,000. That has to do with the amount of weight that the plane can carry. I'm going to toggle back just to remind us of that. Our aircraft can carry no more than 60,000 pounds, so less than or equal to 60,000. And the weight comes from the bottled water, which is 20 pounds, and the medical kits, which are 8 pounds. The fourth constraint is x plus y is less than or equal to 6,000. I'll toggle back here to remind us of where this comes from as well. Each plane can carry no more than 6,000 containers and kits all together. So that's both containers and kits. So the sum of the number of containers of water and the number of medical kits has to be less than or equal to 6,000. To solve a linear programming problem, we first graph the constraints, and then we determine the vertices of the constraints. Once we've determined the vertices of the constraints of the feasible region, we plug those vertices into the objective function, and one of those vertices will minimize the objective function, and one of the vertices will maximize the objective function. So here's the graph of the constraints. So the purple region here is our feasible region. The vertices mean the same thing they mean in geometry. This would be a vertice right here. This would be a vertice of the feasible region right here. This is a vertice, and this is a vertice. So we have 4 vertices in all. And again, the cool thing with linear programming is that one of these vertices will maximize the objective function. One of these vertices will minimize. So how do we find these vertices? Well, some of them can be visually identified, and in fact, we'll do that now. If I'm looking at my x-axis and y-axis here, I see that this is the ordered pair 0, 0. So one of the vertices is no medical kits on the y-axis, no containers of water on the x, and we can see that visually. We can see this vertice visually also. This is x is 0, y is 6,000. So no containers of water, 6,000 medical kits. This vertice here, we can also identify it. This is 3,000 containers of water and no medical kits. The fourth vertice we cannot see very well. Appears to be a little more than 1,000 containers of water and somewhere between 4,000 and 6,000 containers of medical kits. So where do these vertices come from? And how can we identify this one that we haven't seen visually? Well, this vertice would be created by the intersection of this line right here and this line right here. Well, anytime we want to find where 2 lines intersect, that forms a system of linear equations. So to find this ordered pair here, we'll solve the system of linear equations formed by this equation and this equation. Okay, we can see that this equation is the x plus y is less than or equal to 6,000. I'm identifying the y-intercept here for that, and we can see that then that this would be the second equation for our weight. If we couldn't have identified these other vertices, you'll note that they all come from intersecting lines, and so we could have solved systems of equations to find those as well. Okay, so far we have the vertices 0, 0, 0, 6,000, and 3,000, 0. The fourth one will be found by solving the system of equations formed by x plus y equals 6,000 and 20x plus 8y equals 60,000. Notice that these are 2 of our constraints, but we are able to write equals here because we are going to solve the system of equations to find that ordered pair where they intersect. We'll use substitution to solve this. So first I will isolate y, and I get y is 6,000 minus x. Second, I will substitute y's second name, its equivalent name of 6,000 minus x,